Hello, my name is Rachel Greenberg, and today I'm going to be going over my chemistry honors project. So everything that I'm going over is with the equation above. I'm going to be going over the details of each element in the equation. I'm going to be balancing the chemical equation. I will be calculating the enthalpy reaction and seeing if it is endothermic or exothermic. And then I'll be determining how much energy is released or absorbed with the reaction. And I will also be calculating the temperature of water. And with that, I will be determining the phase change of the equation. In my equation, there are three elements, and these are just some of the details of each element. So there's carbon, hydrogen, and oxygen. So carbon's atomic number is 6. Its most common isotope is 12 and 13. It's part of group 14 and period 2. It's part of the non-metal and carbon family. Its electron configuration is 1s2, 2s2, 2p2. It has 4 valence electrons and 2 energy levels. Hydrogen has an atomic number of 1. Its most common isotope is 5. It's part of group 1 and period 1. It's part of the non-metal and it does not have a family. Its electron configuration is 1s1. It has 1 valence electron and 1 energy level. Oxygen has an atomic number of 8. Its most common isotope is 16. It's part of group 16 and period 2. It is in the non-metal and oxygen family. Its electron configuration is 1s2, 2s2, 2p4. Oxygen also has 6 valence electrons and 2 energy levels. Moving into a little more detail on the electron configurations, carbon's electron configuration is 1s2, 2s2, 2p2. Hydrogen is 1s1 and oxygen is 1s2, 2s2, 2p4. And in order to find these, you're going to need the number of electrons per element. And you can use the table on the bottom right and the bottom left and the diagram on the bottom right to figure out what the electron configuration is going to be. So there are a total of 7 energy levels, and each energy level contains sublevels, which is S, P, D, and F. Each sublevel contains orbitals, and those orbitals are regions of space where the electrons are likely to be found. And each sublevel has a different amount of orbitals. So S has 1 orbital, P has 3, D has 5, and F has 7. And an orbital can hold up to a maximum of 2 electrons. And so that makes sense because so S has 1 orbital and the max of electrons it holds is 2. And there's 2 electrons per 1 orbital. So then 3 orbitals, 2 electrons per orbital makes 6 electrons maximum, and then 5 times 2 is 10, and 7 times 2 is 14. So when electrons occupy orbitals, they try to have the lowest amount of energy possible. So we can use the diagram on the bottom right to help determine what orbital the sublevels will be occupied by electrons. So we start at the top and we go down the arrows one by one. So we fill in our number of electrons in through these arrows until we don't have any left. So if carbon has 6 electrons, we start at the top and we put 2 electrons into 1s because S only holds a maximum of 2 electrons. Then we go down to the next arrow. On 2s is another s orbital, so that holds another 2 electrons. And we go down to the next orbital, which is 2p, following the arrows. And we only have 2 electrons left because we've already used 4 of them, and carbon has 6 electrons. So those remaining 2 electrons go into 2p, even though p holds a maximum of 6 electrons. We only have 2 left, so we put those 2 into 2p. And hydrogen has 1 electron, so we only put 1 into 1s. And oxygen has 8 electrons, so it's the same thing. You put 2 electrons into S because it holds 2, then 2s because it only holds 2 electrons, and then 2p we put 4 because that's how many we have left. If we had an element with a higher number of electrons, we would follow down the arrow and put 6 electrons into 2p and continue on to 3s and how many electrons fit into there. Now I'm going to balance the equation. So the top equation, the reactants are on the left side, which are CO2 and H2O, and the products are on the right side. So those are C2H4 and O2. When balancing an equation, you want to lay out everything that you have. So I made a little table that displays how many atoms of each element there are. So there was 1 atom of carbon, 2 atoms of hydrogen, and 3 atoms of oxygen before I balanced it. And then on the right side, where the products are, there was 2 atoms of carbon, 4 atoms of hydrogen, and 2 atoms of oxygen. So what I did to balance it out was I had to multiply the coefficient by the subscript. The coefficient is the big number to the left of a letter. So at the balanced equation on the bottom, it says 2 CO2. The 2 on the left, the big 2, is the coefficient, and the 2 on the right, which is smaller and down a level, that is the subscript. So I had to multiply that coefficient to subscripts. And if there is no subscript next to a letter, that means it has a subscript of 1. So in order to balance out the equation, I had to find which coefficients to multiply each element by in order to get them to be the same on each side. So right now, what I had to do was multiply CO2, on the top equation, I had to multiply the coefficient of 2 to CO2 in order to balance carbon, the reactants carbon with the products carbon. So multiplying that by 2 creates 2. And then then I would also have to multiply that to the O2. So you can't just do 1, you have to do the whole entire group. So 2 times C with the subscript of 1 makes 2. So then I crossed out the 1 and I put a 2 there. And then that changes how many atoms there are of oxygen. So 2 times oxygen with the subscript of 2 makes 4. But then you also have to add that 1 subscript of oxygen to what you have now. So now there are 5 atoms of oxygen, and then you have to balance out hydrogen so that it matches, so that they both add up to 4. So I had to multiply 2 to the reactants hydrogen, and 2 to the subscript of 2 is 4, and then you also have to multiply the oxygen by 2. So on the left side of the reactants, there were already 4 atoms of oxygen, and then with this other 2 times oxygen with a subscript of 1, that comes 6. So you cross out the 5 and put a 6. And then on the product side, you have to match the oxygen with the oxygen, because now the oxygen on the reactant side is 6, but the oxygen on the product side is still 2. So we multiply that last element on the product side. We have to multiply O2 to the coefficient of 3, because a coefficient of 3 times the subscript of 2 is 6, and that matches up with the number on the reactant side. So after doing all of that, you have to keep track of which coefficients you put where, and then I ended up with the balanced equation of 2 CO2, 2 H2O for my reactants, and my products were C2H4 and 3 O2. Now we are moving on to the calculation of the enthalpy reaction, and the equation we are using in order to do that is the change in heat of reaction equals the sum of the change of heat of products minus the sum of change of heat of reactants. And each compound, which is 2 or more elements paired together, each compound has their own enthalpy formation. And in the graph table that I made at the bottom, you can see each formation for each compound, which I just searched up using links that Mr. Thompson posted on Edmodo. So now we're going to calculate the enthalpy reaction, and for each compound I replaced it with its enthalpy formation. So instead of having CO2, I replaced it with its enthalpy formation, which is negative 393.509, and so on and so forth. I replaced all of the compounds with their enthalpy formation, and then I multiplied the coefficient to the enthalpy formation. So I did that for each compound if it had a coefficient, So then that simplified. Now we're on the second line where it says negative 787.018. So I'm added together the reactants and I added together the products, and that simplified down to negative 1,358.618 on the reactant side, and the products simplified down to 52.3. And with the equation that I discussed with you before, which is the change in heat of reaction equals the sum of the change in heat of the products minus the sum of the change of heat of reactants. So basically what we're going to do is we're going to take the products, which are usually in the back of the equation, and we're going to move that up to the front, and we're going to subtract the reactants from the products. So we're taking 52.3 and moving it to the front, and we are going to subtract negative 1,358.618, and when you subtract a negative, that becomes addition. So it's basically 52.3 plus 1,358.618, and the change in heat that I got for my final answer is 1,410.918 kilojoules per mole. And this is an endothermic reaction because it is a positive number, and that means that the water is going to be gaining heat, and an endothermic reaction means that it is taking and absorbing energy or heat. So now we are going to find how much energy is released or absorbed if about 250 moles of product is created. So with this, what we're going to do is we're going to multiply 250 moles by the enthalpy reaction we previously found, which is 1,410.918 kilojoules per mole. And you multiply these together, and because both of the numbers have mole as a unit, those cancel out, and then that means kilojoule is the only unit that will be in our answer. So 250 times 1,410.918 is 352,729.5 kilojoules for our answer. Now we are going to calculate the temperature of the water. So some of the variables that we're going to be using for this are specific heat capacity of water, mass of water, and temperature of water. So the specific heat capacity of water in liquid form is 0.00418 kilojoules. Then the mass of water is 1,000 grams, and the temperature of water is 21 degrees Celsius. Now we are going to be calculating the temperature of the water, and we are going to use the equation Q equals m times C times delta T. In our equation, Q is equal to the heat energy, and we solved for this a couple slides ago when we were solving for the energy released / absorbed if 250 moles of product is created. And we got a positive number for that, but in our equation, it's negative 352,729.5 kilojoules. The reason why we switch it to a negative is because if the water is absorbing energy from the product because it's an endothermic reaction, then that means the product is going to be losing energy, and to signify that, we have to put a negative symbol in front of the number so that it shows it is decreasing. And then M in our equation is mass, and that is 1,000 grams for the mass of the water. C is the specific heat capacity of liquid water, which is 0.00418 kilojoules over grams. The change, delta T, which is the change in temperature, is what we are solving for. So we are just going to put a degree Celsius in our equation for the time being. And we're just going to solve this with some simple algebra. So we are going to multiply 1,000 grams times 0.00418 kilojoules over grams first. And because each number has a unit of grams, they're just going to cancel out when you multiply. So that simplifies to 4.18 kilojoules because the grams are now gone. And then more simple algebra, we are just dividing 4.18 kilojoules from both sides. And when we divide negative 352,000 by 4.18, they both have the unit of kilojoules. So you have to, those cancel out again. So now we just have a degrees Celsius is equal to negative 84,385.04785. So that is the temperature of the water after undergoing the product. And now we are solving for the change in temperature. So in order to do that, you take the final temperature of the water minus the initial temperature of the water. So if the final temperature, which we just solved for, is negative 84,000, we subtract 21 degrees Celsius because that is what the temperature of the water was before. So once you do that, the change in temperature is negative 84,406.04785. And the reason it is a negative number is because it goes from a positive, the temperature of the water goes from a positive number to a negative number. And if you were to subtract the change in temperature from the initial, then you would get the final. So that is how you solve for the temperature or the change in temperature of the water. Now there was a phase change from liquid to solid. Our water started off as a liquid at 21 degrees Celsius, and anything between 0 and 100 degrees is a liquid. So the water was in liquid form, and then after undergoing the product, the final temperature was negative 84,000, and because it's a negative, that means it's in the solid category. So there was a phase change of freezing, and it went from 21 degrees to negative 84,000 degrees. This concludes my chemistry honors presentation. Thank you for listening.